already we've seen an example problem worked where we did a differential equation to find the velocity function and the position function from the acceleration using initial conditions. Here we are going to look at an example problem where the acceleration depends on not just the time but the velocity as well. And we're going to solve this differential equation with separation of variables like we did before. It's slightly more complicated when we have the dependence on velocity and time. Before, we've only solved differential equations where the acceleration depended on time alone, but the process is extremely similar. Situations where we might see an acceleration where it depends on velocity and time are when we talk about drag or air resistance. Objects that are subject to air resistance and drag, a lot of times as velocity increases, then the force of the drag increases. And since force determines acceleration, that means the acceleration is affected by an increasing velocity. So the acceleration is going to depend not just on the velocity, but on the time as well. So here's our acceleration equation. We have a of t is equal to 3t over the velocity squared. And we need initial condition to solve for our constant of integration, and that is the velocity at time 0 is equal to 2 meters per second. Now this is not an actual drag situation. This is somewhat easier to solve. We will get to a point where we work on drag situations, but first let's just work on solving differential equations. So we know that the acceleration is equal to the derivative of velocity with respect to time, and that's equal to our 3t over v squared. So now again, separation of variables says we get everything with a v on one side and we get everything with a t on the other. So let's multiply both sides by dt, and let's multiply both sides times v squared. So that's going to get rid of our dt on the left side, and it's going to get rid of our v on the right side and move everything over. So we've got v squared dv on the left, and that is equal to 3t dt on the right. Let's go back to writing in black. Okay, so now to get rid of the dv and the dt, we're going to integrate both sides. So let's take the integral of both sides. On the left side, we are integrating with respect to the velocity. On the right side, we are integrating with respect to the time. So the integral of v squared is going to be 1/3 v cubed plus, let's call it c1. And on the right side, we're going to have 3/2 t squared, and we'll call that one c2. Moving the c1 over to the other side, we've got c2 minus c1, and c2 minus c1 is just another constant of integration. Let's call it c. So now we've got 1/3 v cubed is equal to 3/2 t squared plus c. Okay, well, we need to solve this thing for v because we're looking for a function of velocity with respect to time. So let's go ahead and move everything that is not v over to the right hand side. So we will multiply by 3, and we're also going to take the cube root of both sides. Okay, so what that's going to do is give us a v on the left, and we are going to have, let's see, we multiply by 3, so that's giving us a 9/2 t squared plus c, and we've got the whole thing cube rooted. Great, so now we have velocity, but we need to take care of our constant of integration. That's where we go back to our initial condition, which was the velocity at time 0 is equal to 2 meters per second. So plugging those values in, the velocity is 2, and we have the cube root of 9/2 times 0, because this is times 0, squared plus the constant of integration. All right, let's move this initial condition. We just want to move the initial condition. Come on. Oh, it's going to make me do the whole thing. Okay, let's erase the initial condition then. And we will cordon off over here. We're going to use this to solve for our C up here. So let's see here. We've got 2 is equal to the cube root of C eventually, because that 0 makes the 9/2 go away. And let's cube root, or raise each side to a power of 3. So we've got 2 times 2 is 4 times 2 is 8 is equal to C. Fantastic. Now we can plug that into our original equation, and we have V of t is equal to 9/2 t squared plus 8, and let's just be a little professional about this and raise it all to the 1/3 power, which, as you know, is the same as a cube root. So there it is, beginning to end. The only added difficulty that you had was when you've got your separation of variables for this stuff, now we have an actual integration on the left and on the right, whereas previously we only integrated on the right because we just had a dv on the left. All right, so not much more. Here is the problem that I want you to work for homework. We are going to have a of t equal to t over 2v, and our initial condition is going to be v naught is equal to -5 meters per second. So go ahead and solve that using separation of variables, and we'll see what you end up with for your v of t. Oh, let's add one more thing. Find for me what is the velocity at, let's say, 8 seconds. All right, see you later.